Hello, we're going to be testing the cam and crank position sensors on this 2006 Toyota Corolla. We want to move over to the vehicle and show you where they are. Right here is our connector for our crank. As you see, we have back probe. And we're going to be reading all our measurements at with our picoscopes today. Move over to the right. We have one of our cam position sensors. And then back over to the left, we have, this is a cam position sensor for the variable valve timing. And you may have noticed with all of these sensors, we do have two wires, meaning we're going to have a variable reluctance type. We're going to be looking for an AC output. For variable reluctance, how that works is there's a wheel that has teeth on it, and next that is the sensor, which is basically a magnet with a coil wrapped around it. As each teeth passes the sensor, it interrupts that magnetic field, inducing a voltage into that coil, which is sent out to the PCM. Some of the tests we're going to be demonstrating will show with our picoscope readings, and we'll explain along the way.
We have our Pico leads hooked up to our camshaft position sensor, both leads connected, and then we have it connected to our crankshaft position sensor down here. And we're going to be recording it at idle and at 2500 RPM to show the relationship between the two sensors.
Looking at this scope graph, we have two waveforms. The red one on top is our non-VVT CAN position sensor, and underneath, our blue waveform is our crank position sensor. If we count the peaks of the red waveform, we have 3 peaks. That would be representing the 3 teeth on the CAN reluctor wheel. This long length area would represent the one missing tooth for position. And when counting the blue waveform, we have 34 peaks with a 1 or 2 tooth gap. With 36 teeth, we would have 1 tooth for every 10 degrees of crankshaft rotation, and according to the 4-stroke cycle, we have 2 crankshaft rotations for every 1 rotation of the camshaft, which is demonstrated here. So here is 1 cycle or rotation of the crankshaft. Then we have 1 more rotation here where that cuts off. That represents as 1 camshaft rotation up here. So next we're going to look at the waveform of an engine that's going at 2500 RPM. With this scope graph represents our cam position sensors with the engine at a speed of 2500 RPM. From here you can see that the frequency of both sensors did increase, but when you zoom in, you can see that there are still 2 crankshaft rotations for every 1 rotation of our camshaft.
For this demonstration, we backprobe the coil pack for spark plug number 1 to the ignition timing signal, which Toyota calls it, right here to the red and light blue wire, and then we grounded it over here just to the engine block. We did this to see the relationship between when the spark plug fires in the first plug and the crankshaft rotation position for just one of the packs. This will be shown on the Pico measured at idle and at 2500 RPM.
With this graph, we still have our crank position sensor being this blue waveform here at the bottom. Above it is our ignition signal voltage, showing when cylinder number 1 is firing at the very start of the power stroke. As you can see, spark plug number 1 is firing once every 2 crankshaft rotations. And when we count the blue peaks, the spark plug fires between the 20th and the 22nd peak here. Next, we'll take a look at these two waveforms when the engine speed is at 2500 RPM. Taking a closer look at our crank position sensor and our ignition signal voltage waveforms with the engine speed at 2500 RPM, we see that as the engine speed increases, the frequency of our crankshaft rotation increases as well, which will lead to the spark plug firing more. Despite the frequency increase, we still show that the plug is firing once for every 2 crankshaft rotations. So for today, our demonstration is going to be performed on this classroom model here. It is a 2007 GM Ecotech 2.2 liter. Just to show you a little bit of the functionalities here. Up front, starting with this board, we have our controls and switches. We can adjust like the engine coolant temperature, manifold absolute pressure, mass airflow, intake air temp, engine speed, and then we can change what our O2 sensor is reading. Over here to our right, we have these pinouts for the ECM where you can hook up your DVOM, and then all the way to the bottom here is our ignition. So just to show you how cool this is, you can actually see sparks and fuel as you run this. So over here in the middle we have our crank and cam position sensors. This is our reluctor wheel for the crank, and over here is our cam. Since we have the cam entrapped in this plexiglass here, or plastic, we will not be back probing it today, we'll just be looking at the crank. My setup, you'll see we'll have our picoscope reading, and then we have hooked up our scan tool to let me know what our engine speed is. Here we have our schematic for the classroom model. In the center we have our 3 wires cam and crank position sensors. Since they are 3 wire circuits, we do expect to see a digital waveform on our picoscope. It's hard to tell here, but this light green circuit is our 5-volt reference. In the middle we have a purple circuit, which is our low reference / ground. And here, this yellow circuit is our signal wire, which is going to be back probed so we can see our scope pattern on the picoscope. Right now we are at about 500 RPM. We'll turn it up. You can see the reluctor wheel spin faster as I turn up the engine speed. We are about 680 RPM right now. I'm going to go in the opposite direction. I'm going to turn the engine speed down. We are about 230 RPM. And we'll see those reflected in our picoscope readings as well. Just to recap on what we saw today in our lab demonstrations, we saw relationships between a crank position sensor with a cam position sensor, as well as a crank position sensor with the ignition coil on cylinder number 1 on a 2006 Toyota Corolla. On a picoscope, we saw analog signals that we had demonstrated with idle and at 2500 RPM. We saw as the engine speed increased, so did the frequency of our crankshaft waveform. We also saw that when you counted the peaks of each waveform, that represents the number of teeth on each reluctor wheel. These signals that were demonstrated are what the PCM sees to determine where the crankshaft is at, and what stroke each cylinder is with the crankshaft position sensor. These signals can be used for misfire diagnostics with OBD2 systems, ignition timing, fuel injection on sequential fuel systems, and they also serve as inputs for other vehicle features like traction control. We also took a look at what a digital signal looks like for a crankshaft position sensor on a 2007 GM model engine. Hopefully you found these demonstrations as cool as I did, and you have a wonderful day.